Hey everyone, and a huge welcome to this explainer. I am super excited you're here today because we're diving into a genuinely fascinating piece of physics history, straight out of the WASSCE Physics archives. Now, before we really get our hands dirty, I've got to give a quick shout out to our source material for today, QandAHelp. If you're not already in the loop, QandAHelp.com is basically the ultimate reviewer-checked prep platform for anyone gearing up for major West African standardized exams. We're talking WAEC, NICO, JAMB, the whole shebang. They take all these scattered, intimidating past questions and organize them into this beautifully clear library. So today, we're going to lean on their awesome study tools to break down a very specific, kind of tricky puzzle. Let's just jump right in. So here is the exact question we're looking at. Question 4 asks about gravitational field intensity, and it throws 3 distinct claims our way. Roman numeral 1, it is a scalar quantity. Roman numeral 2, it's greatest at the poles. And Roman numeral 3, it is exactly 0 at the center of the Earth. Our job is to figure out which of these statements is actually correct so we can pick the right option. Treat it like a mystery we get to solve step by step. Let's start investigating.
Okay, first things first. To crack this, we need to know what gravitational field intensity actually is. Mathematically, you'll see it as G equals F divided by M. In plain English, it's the gravitational force acting per unit mass. Think about it like this. Imagine a student standing outside. Even though they completely can't see it, there's this massive invisible pull acting on their body, constantly drawing them downward. That pull has a specific strength, and, this is absolutely crucial, it's pointing in a very specific direction, straight down toward the planet.
Right, so keep that downward pull in mind while we do a really quick refresher on 2 fundamental physics concepts. We have scalar quantities, which are all about magnitude. That's just a size or an amount. Think temperature or mass. But then we have vector quantities, which have both magnitude and a specific direction. Now, because that invisible gravitational pull we just talked about has a specific strength, that's its magnitude, and it always points directly towards the center of the Earth, that's its direction, it inherently has a directional component. It's a package deal. You literally cannot separate gravity from the direction it's pulling you.
And bam, just like that, we can totally bust our very first claim. Statement 1 tried to tell us that gravitational field intensity is a scalar quantity. But since it absolutely requires both magnitude and a direction toward the Earth's center, it is undeniably a vector, no question about it. So we can confidently write off Statement 1 as completely false.
Moving right along to test statement 2. This one claims gravity is greatest at the poles. To figure this out, we actually need to look at the shape of the Earth itself. Our planet is not a perfect sphere. Actually, scratch that, it's kind of squashed. It's slightly flattened at the north and south poles and bulges out around the equator. What this means is that the distance from the surface down to the exact center of the Earth, which we call r, is physically smaller at the poles. Now looking at the math, gravitational field intensity, G, is proportional to 1 over r squared. Basically, as the distance shrinks, the intensity shoots up. Since that distance is smallest right at the poles, the gravitational pull there must logically be at its maximum. So statement 2, totally true.
Which brings us to our final test, statement 3. This one is super interesting. Imagine you could somehow tunnel all the way down and stand at the exact boiling core of the Earth. What happens to gravity? Well, the entire mass of the Earth is now completely surrounding you. Gravity from the top half pulls you up. Gravity from the bottom half pulls you down. Left pulls left, right pulls right. Because you are dead center, every single upward pull is perfectly canceled by a downward pull. Your net resultant force just becomes 0. And if we look back at our formula, if force is 0, then 0 divided by whatever your mass is still exactly 0. Statement 3 is incredibly true.
So, let's take a breath and bring this all together. Statement 1, false. It's definitely a vector. Statement 2, true. Gravity really is greatest at those flattened poles. And statement 3, also true. Gravity completely cancels out to 0 right at the center of the Earth. All right, now let's use some seriously smart exam strategy. We already proved beyond a doubt that statement 1 is false. So, any multiple choice option that includes Roman numeral 1 has to be wrong. Watch this domino effect. Step 1, we cross out option A, gone. Step 2, option B has it, so that's gone. Step 3, option D includes all 3 statements, so we toss that out too. Just by knocking out that one false statement, we are left with only one logical survivor.
Yep, option C is our clear winner. Statements 2 and 3 only. You know, it is incredibly satisfying to nail an answer not by just taking a wild guess, but by truly understanding the mechanics behind it. Mastering this WAEC past question isn't just about memorizing one solution, it's about building that bulletproof exam confidence so you can handle literally whatever they throw at you. But hey, before we move into quiz mode, I want to drop a couple of massive QandAHelp shortcuts to save you precious time on exam day. First up, the vector check. If a physical quantity ever needs a direction, like pointing towards the core, you instantly know it's a vector. Don't overthink it. Second, the Earth check. Just lock these extremes into your brain. At the poles, gravity is at its absolute greatest. At the center, gravity is a big fat zero. Memorize those, and you can skip the long calculations entirely.
All right, active recall time. Let's lock all of this in with some rapid-fire questions. Quick quiz number 1. Is gravitational field intensity a scalar, a vector, a dimensionless, or a constant quantity? Think back to that invisible downward pull we talked about.
If you said vector quantity, you absolutely nailed it. Because that gravitational pull has both a magnitude and a very specific, undeniable direction toward the Earth, it is a textbook vector.
Awesome. Let's see how you handle the next one. Quick quiz 2. At which location on the Earth's surface is gravitational field intensity generally greatest? Remember what we said about the slightly squashed shape of our planet? The answer is the poles. Because the Earth is slightly flattened out at the top and bottom, standing at the poles means you are physically closer to the exact center of the planet, and a shorter distance means a stronger gravitational intensity.
You are doing great. One last check on Earth's core mechanics to bring it home. What is the gravitational field intensity at the exact center of the Earth? Imagine yourself standing right in the very middle of everything.
Boom! The answer is 0. Huge congratulations if you got that one right. Because equal mass surrounds you on every single side, those gravitational pulls act in perfectly opposite directions and completely cancel one another out, leaving you with 0 net force. What a fantastic session today. Let's do a really quick, snappy wrap-up. We discovered that statement 1 is false because gravitational field intensity is a vector, not a scalar. Statement 2 is true because the flattened poles are closer to the center, making gravity the strongest there. And statement 3 is true because at the exact center of the Earth, all pulling forces just cancel out to 0. That confidently left us with option C. Listen, if you found this step-by-step breakdown helpful, I highly recommend heading over to QandAHelp.com and setting up a free learner account. They have this massive library of reviewer-checked explanations just like this for WAEC, JAMB, and NICO, and it will give you all the tools you need to really level up your prep.
But before you go, I want to leave you with a completely wild thought experiment to chew on. We just established that gravity pulls everything toward the Earth's core, right? But we also just proved that at the exact core itself, gravity is perfectly 0. So, what exactly would happen if you dropped an apple into a tunnel drilled all the way straight through the planet? Would it just stop in the middle? Would it shoot out the other side? Think about it. Keep that curiosity alive, keep asking those big questions, and I will see you in our next explainer.